Welcome back, Level 2 NCEA Physicists, continuing on with the nuclear internal. Today looking at energy and mass defects. So in order to understand what's happening inside of the atom in terms of energy considerations, we need to have the concept of the atomic mass unit. So the atomic mass unit is defined as 1/12 the mass of an isolated carbon-12 atom. So what is the mass of one isolated carbon-12 atom? Well, 1 mole of carbon atoms is 0.012 kilograms. Okay, so 1 mole is 6.023 times 10 to the 23. So if you have 6.02 times 10 to the 23 carbon atoms, it will weigh 0.01 or have the mass of 0.012 kilograms. So therefore, to work out the mass of, or the atomic mass unit, we have to work out the mass of one carbon atom. So it'll be 0.012 kilograms divided by 6.023 times 10 to the 23, which is Avogadro's number, which then gives you the mass of one atom, which is going to be 1.99 times 10 to the negative 26 kilograms. We then divide that number by 12 to get the 1/12, which gives you the atomic mass unit of 1.661 times 10 to the negative 27 kilograms. Okay, basically the mass of the combined nucleons. Okay. So in terms of atomic mass unit, we also have to know the mass of the electron. Okay, so it's about 9.1 times 10 to the negative 31 kilograms, which is a lot lighter than the proton and neutron. And you can see the neutron is basically the mass is slightly more than that of the proton, because it's seen essentially as being a proton plus an electron. And then we also have the atomic mass unit we've just calculated. So in terms of Einstein's famous equation, mass and energy are different sides of the same coin, so different manifestations of the same thing. So energy can be transferred into mass, and mass can be transferred into energy. And that's the famous equation, E equals mc squared, where E is energy in joules, mass is mass in kilograms, okay, m is mass in kilograms, and c squared is the speed of light, all squared, 3 times 10 to the 8, all squared. So what is the energy equivalent? So how much energy is in 1 gram of matter? We just plug the numbers in, so it'll be the mass will be 1 divided by 1,000, because remember we're converting grams to kilograms, times 3 times 10 to the 8 all squared, which will give us a value of approximately 9 times 10 to the 13 joules. Quite a lot of energy. So remember, U matter, unless you multiply yourself by time speed of light squared, then U energy. So this is the interesting thing, okay, so 1 plus 1 actually equals greater than 2 in nuclear physics, okay, so if you calculate the sum of all the different nucleons and the electron, so basically the protons, neutrons, and electrons, you add the masses together, you get a total mass of the atom of around about 2.009 times 10 to the negative 26 kilograms. Okay, and then you compare that with the calculation that you've used for your atomic mass unit. Okay, so that's going to be basically 12 times the atomic mass unit, the protons and the neutrons. And you'll see there's something called a mass defect. There's a difference in the mass. Okay, so you calculate the mass of a carbon-12 atom using the atomic mass unit, you get 1.993, so that's the actual atom itself. Yet the substituent parts, the individual protons, neutrons, and electrons, equal up to 2.009 times 10 to the negative 26. There's a difference in mass between the different parts that make up the atom and the atom itself of 1.6 times 10 to the negative 28 kilograms. A small difference, but in the size of atoms, quite large. So what happened to this extra mass? Well, it got transferred into energy. So what kind of energy? It's the binding energy. Okay, so the binding energy is the energy required to separate all the nucleons, or conversely, with the example we've just had, the energy that is released when the different nucleons are combined, the protons and the neutrons, to form the nucleus. Okay, that's known as the binding energy. So in terms of the mass defect for our example of the carbon atom, therefore the energy, or the binding energy associated with the carbon nucleons all combining up to make the carbon atom, it's around about 1.48 times, 1.44 actually, times 10 to the negative 11 joules. Again, a small number, but considering it's only one atom, that mounts up. Okay, so there it is. So that means that the binding energy per nucleon is going to be that number divided by 12, which is 1.23 times 10 to the negative 12 joules. And you can use that number to actually, if you plot the different number of nucleons in the nucleus, so that's basically the atom, against the average binding energy of the nucleons, you get this plot here. And basically, the higher the energy per nucleons in the nucleus, the more stable that isotope is. So iron 56 is the most stable isotope in the universe. So eventually the entire universe will convert into iron 56.